All right, for this final example of section 6.4, the shell method, I already have a sketched. Here we've got the function y equals 4 over x on the interval 1 to 4, and it's this volume, or sorry, excuse me, it's this area that we are to rotate about the x-axis and find its volume. So this is a problem this is a geometry that I would recommend actually not using shell method on if we are just trying to go about it the most efficient way. But these problems are really good to take a look at and do them in maybe the less efficient way at times so you can learn when to use the shell method and when to not use the shell method, or any other method for that matter, when to use the disk or washer method and when to not use those methods. That's one of the biggest things that students struggle with with this section is once they have the methods, disks, washers, or shell method, they find themselves with a geometry and they're not sure which one to do. Well, really what you do is always sketch the region and then just pick a method and start figuring out what you'd have to do. Don't do anything crazy, just try to figure it out. And if you find yourself doing a couple things that we'll talk about in this problem, and we have talked about in previous examples and previous videos, that might be a sign to you to switch it up. Okay? And then after this example, there will be one more video that I do. It's not a specific problem, but it is a comparison of disks, washers, and the shell method. So if we use the shell method here, we are rotating about a horizontal axis, so we need to integrate with respect to y. Okay? So if we do this, for shell method, we need to draw a slice in our region that is parallel to the axis of rotation. So if I draw my slice here, then this distance right here, that would be the radius, and then the length of this line segment would be the height. Well, the height here is clearly going to be this x value of 4 minus this x value of 1. So the height for this region will be 4 minus 1, so 3. But notice what happens here. I'm going to go ahead and draw this little dividing line here. So down here, I'll call this region 1, and up here, I'll call this region 2. If I draw another slice parallel to my axis of rotation, which is what's required if we're using shell method, the radius doesn't change. This is still connected or tethered. This measurement is still tethered to the x-axis. So because it's tethered to the x-axis, we are allowed to call that y, so that value is still the same. But what is changing is the x value on the right-hand side is different than the x value on the right-hand side down here in region 1. And that's because the function that's on the function that constitutes the right boundary changes depending on your y value. So because our integrand will change depending on as our y values vary, and we're integrating with respect to y, so that means we're going to need two integrals if we integrate with respect to y. So that means we'll need an integral for the bottom half and an integral for the top half. So this is exactly why the disk method is much better. The disk method, you only need to worry about the radius. There's no height. So you just measure from your axis of rotation, and it doesn't matter what x value you measure your radius at. You can pick this x value and measure up. You can pick this x value and measure up. But no matter where you go, this curve is always the curve that you go to. So the radius for the disk method is just 4 over x, and the volume is pi integral 1 to 4, 16 over x squared dx. And that's it. For the shell method, we have to split this up. Okay. So to split this up, we already have our two regions written down. So for region 1, the radius is just the y value, and the height is 4 minus 1, so 3. For region 2, I guess I'll draw the... Actually, no, we'll go ahead and just... For region 2, the radius is still the same. That's y. But this time, the height is our function. So our function, our curve here, is y equals 4 over x. So we can just rearrange that and solve for x to get 4 over y. So this becomes 4 over y minus 1. That's our height. So the total volume, so basically doing the integral once here, doing the integral here once, and then adding them together. I guess I don't need to really write total. That's sort of implied. This volume v would be 2 pi the integral from 0 to, what is this intersection point? Well, if we plug in 4, since this is x equals 4, if we plug that into our function, we get 4 over 4, which is 1. So the y value here is 1. So we'd go from y equals 0 to y equals 1. So let's just write that out as 1. And we'd also need to figure out what that intersection is. So this would be 0 to 1, radius, which is y, times the height, which is 3, dy, plus 2 pi times the integral from 1 to this intersection point, which is going to be, this is x equals 1. So if we plug this 1 into this x, we have 4 divided by 1, which is 4. So this y value up here is 4. Okay, then our radius again is y, and our height this time changes to 4 over y minus 1 dy. So that is the total volume.